Welcome to today's session, where we'll tackle an exciting problem from LeetCode titled Making a Large Island, problem number 827. This is a fascinating challenge that tests your ability to manipulate grids and apply graph-like techniques. By the end of this walkthrough, you'll have a deeper understanding of the problem and learn efficient strategies to solve it. Let's dive in. In this problem, you're working with an nxn binary matrix called grid, where each cell can either be 1, representing land, or 0, representing water. An island is defined as a group of ones that are connected horizontally or vertically, also known as four-directional connectivity. The task is to determine the size of the largest possible island you can create in the grid by changing at most one water cell, represented by 0, into a land cell, represented by 1. You need to return the size of this largest island as an integer. The input consists of the grid itself, which is guaranteed to be square, with dimensions ranging from 1 by 1 up to 500 by 500. Each cell in the grid is either 0 or 1. The output is an integer representing the size of the largest island after making the one allowed change. Let's look at the first example. Here, the input grid is a 2 by 2 matrix where the top left and bottom right corners are land cells, and the other two cells are water. Currently, the grid contains two separate islands, each of size 1. If you change the water cell at position 0, 1, or 1, 0 to land, these two islands will merge into a single island of size 3. Hence, the output for this example is 3. This demonstrates how flipping one water cell can maximize the size of the connected land. In the second example, the input grid is also 2 by 2, but this time 3 of the cells are already land, forming an island of size 3. By flipping the water cell at position 1, 1 to land, the existing island grows to cover the entire grid, reaching a size of 4. Therefore, the output for this example is 4. This case shows how to expand an already connected island to its maximum size by strategically flipping just one water cell. The third example demonstrates a scenario where the entire grid is already land, forming one large island of size 4. Since there are no water cells to flip, no change is needed, and the largest possible island remains the same size, which is 4. Now, consider the problem's constraints and edge cases. The grid is always square, with dimensions ranging from 1 to 500. Each grid cell is either 0 or 1, and there is guaranteed to be at least one land cell. Edge cases include grids that are entirely land, where no changes are necessary, grids with only one land cell, where flipping an adjacent water cell creates the largest island, and grids with only one water cell, where flipping it results in the entire grid becoming land. To begin tackling this problem, one straightforward approach is the brute force method. Here, we explore every cell in the grid, focusing on each 0. For each 0, we simulate converting it into a 1, and then use a search algorithm like DFS or BFS to calculate the resulting island size. Afterward, we undo the change and repeat the process for the next 0, keeping track of the largest island size we encounter. While this method is conceptually simple, it is computationally expensive. Since each DFS or BFS can take n squared time, and we repeat this for every cell in the grid, which totals n squared cells, the overall complexity becomes n to the power of 4. This makes the brute force approach impractical for larger grids, such as when n equals 100, as the processing time grows rapidly. To improve upon the brute force method, we can use an optimized approach based on connected components. Here, instead of recalculating the size of islands repeatedly, we pre-compute this information and reuse it. First, we use DFS or BFS to identify all existing islands in the grid, assigning each a unique ID and recording their sizes in a dictionary. Then, as we iterate through the zeros in the grid, we determine which unique island IDs are adjacent to each 0, using a set to avoid duplicates. By summing the sizes of these adjacent islands and adding 1 for the converted 0, we calculate the potential size of the merged island. Throughout this process, we track the maximum size encountered. This optimization reduces the complexity significantly. Pre-computing the islands takes n squared, and evaluating each 0 also takes n squared, resulting in an overall optimal complexity of n squared. While there are alternative methods, such as using matrix manipulations with prefix sums, these tend to be less intuitive and don't improve the time complexity further. The chosen strategy for solving this problem is the optimized connected components approach using DFS or BFS. This involves two main steps. First, we pre-compute the sizes and IDs of all islands using a graph traversal method. Then, as we iterate through the zeros in the grid, we calculate the potential size of merged islands by referencing the pre-computed information. The largest possible island size is tracked and returned. The core idea here is to avoid redundant calculations by leveraging reusable data. Assigning unique IDs to islands enables us to efficiently determine the impact of merging without recalculating sizes repeatedly. This reduces the complexity from n to the power of 4 in the brute force approach to n squared, making it far more feasible for larger grids. While the brute force method is easier to implement, it's computationally prohibitive. Matrix manipulation techniques, on the other hand, are less intuitive and offer no performance gains. Union find is another option, but it introduces added complexity in managing the data structure, whereas DFS or BFS provides a straightforward and effective solution for this problem. The connected components approach is chosen because it strikes the right balance between simplicity, efficiency, and clarity. By pre-computing and reusing island information, it eliminates redundant calculations and adheres to the problem's constraints effectively. Its n squared time complexity ensures the solution is optimal, even for larger grid sizes. This method is not only efficient but also easy to understand and implement, making it an excellent choice for solving the problem. To solve the problem, we begin by understanding the input and desired output. The input is a grid consisting of ones and zeros, where 1 represents land and 0 represents water. The task is to determine the maximum possible size of an island after flipping exactly one water cell, represented by a 0, into a land cell, represented by a 1. An island is defined as a group of connected land cells linked horizontally or vertically. The output is the size of the largest island achievable through this single flip. The first step in our approach involves identifying all the existing islands in the grid. Using either depth-first search, DFS, or breadth-first search, BFS, we traverse the grid to locate connected components of ones. These components are assigned unique identifiers, referred to as island_IDs. As we traverse, we calculate and store the size of each island in a dictionary called island_sizes. Additionally, we update each cell in the grid with its corresponding island_ID for efficient lookups later on. For every unvisited land cell in the grid, we perform a DFS or BFS to discover all connected cells within the same island. As we explore, we count the total number of cells in the current connected component and update the island_sizes dictionary with its size. At the same time, we label all visited cells with the current island_ID so they won't be counted again. For example, given a grid where the top left island spans 3 cells and there's a separate single-cell island in the bottom right, we would label these islands uniquely. After labeling, the grid might look something like this. The top left island could have an ID of 1, and the bottom right island an ID of 2. Corresponding to this labeling, the island_sizes dictionary would store 1, 3, 2, 1, where 1 refers to the size of the first island and 2 refers to the size of the second. This pre-computation step ensures that we have all the information needed to efficiently evaluate the impact of flipping each water cell. Once the islands are labeled and their sizes are pre-computed, the next step is to explore flipping each 0 in the grid. For every water cell, we calculate the potential size of the island that would form if that cell were turned into land. To do this, we examine its 4 neighbors, up, down, left, and right. Using the island_ID labels, we identify the unique islands adjacent to the current 0. By summing the sizes of these neighboring islands, which we retrieve from the island_sizes dictionary, we estimate the new island size. To avoid double counting, we use a set to track the unique island_IDs of the neighbors. Finally, we add 1 to the total size to account for the flipped 0 itself. During this process, we continuously update a variable to keep track of the maximum size encountered. We also account for special cases, such as when the grid contains no zeros, in which case the largest existing island size is returned, or when the grid contains no ones, where flipping any 0 creates a single-cell island. Small grids are handled carefully to avoid out-of-bound errors during neighbor checks. Pre-computing island sizes plays a critical role in optimizing the algorithm's efficiency. Instead of recalculating the size of islands repeatedly during the 0 flipping step, we compute these sizes once and simply reuse the results. This avoids redundant work and ensures that the algorithm runs efficiently. Labeling each island with a unique identifier is another key optimization. It prevents double counting when evaluating the contribution of neighboring islands. For instance, if two adjacent cells both belong to the same island, the unique island_ID ensures that this island's size is only added once. Additionally, the operation of flipping a zero is localized. Only zeros adjacent to existing land cells have the potential to increase the size of an island. This observation allows us to skip unnecessary computations for zeros that are entirely surrounded by other zeros. Efficient data structures further enhance the algorithm. The 2D grid is used not only to represent the input map but also to store the island_IDs during pre-computation. This labeling enables 1 access to each cell's island_ID during the zero flipping step. The dictionary, island_sizes, maps each island_ID to its corresponding size, allowing constant time access to island sizes as we evaluate potential flips. A set is used during the zero flipping step to track the unique neighboring islands for each zero, ensuring that no island is counted more than once. The algorithm's time complexity reflects its efficiency. Pre-computing island sizes involves visiting each cell once, resulting in a time complexity of m*n. During the zero flipping step, each zero checks up to 4 neighbors, leading to an overall complexity of m*n. The space complexity is also m*n, accounting for the storage of the island_sizes dictionary, the labeled grid, and the recursion or queue space used by DFS or BFS. Together, these optimizations ensure that the algorithm is both time and space efficient. In this implementation, we start by defining the largest island function within the solution class. The input is a grid representing a map of land and water cells, where ones represent land and zeros represent water. The first step is to calculate the size of all existing islands using a helper function DFS. This function performs a depth-first search starting from a given cell, marking all connected land cells with a unique index to distinguish one island from another. A stack is used to explore neighboring cells in all 4 directions, and as we visit each land cell, we update its value in the grid to the current island index and increment the size counter. The function then returns the total size of the island. Next, we iterate through all the cells in the grid. For every unmarked land cell, we call the DFS function to calculate its size and store the result in the island_sizes dictionary, associating it with the corresponding index. We start assigning indices at 2, since 0 and 1 are already used in the grid for water and land, respectively. At this stage, we also initialize max_island to track the largest island found so far, defaulting to the largest existing island size in the island_sizes dictionary, or 0 if no islands exist. Now, we focus on calculating the potential size of the largest island we could create by flipping a single water cell to land. To do this, we iterate through every cell in the grid and examine each zero cell. For each zero cell, we simulate flipping it to 1, initializing potential_size to 1. We then check its neighboring cells in all 4 cardinal directions. If a neighboring cell belongs to an island, identified by an index greater than 1, we add the size of that island to the potential size. To ensure we don't count the same island multiple times, we use a scene set to track island indices we've already added. After calculating the potential size for each zero cell, we compare it to the current max_island value and update if the new size is larger. Finally, we return the maximum island size as the result, which represents the largest island we could achieve after performing one optimal flip. We start by importing the necessary libraries and defining our largest island function. The goal of this function is to determine the size of the largest island that can be created by flipping one zero cell to 1 in a binary grid. First, we initialize the grid size n and create a map, island_sizes, to store the size of each identified island. Each island will be assigned a unique index starting from 2, since 0 and 1 are already used in the grid to represent water and land, respectively. Next, we loop through each cell in the grid. If a cell contains a 1, it means it belongs to an island. We call the DFS helper function to determine the size of the island and assign it a unique index. The size is then stored in the island_sizes map, and we increment the index for the next island. Once all islands are identified, we initialize max island to the size of the largest island found so far. If no islands exist, it defaults to 0. At this point, we prepare to calculate the potential size of new islands by flipping 0 cells. We define the directions for exploring adjacent cells, which include up, down, left, and right. Now, we iterate over each cell in the grid again. If a cell contains 0, we consider flipping it to 1, which could potentially connect multiple islands. To do this, we use a set called scene to keep track of which island indices have already been added to the potential size calculation. We start with a potential size of 1, representing the flipped cell itself. Then, we explore its neighbors in all 4 directions using the directions array. For each neighbor, if it is within bounds and belongs to an existing island, we retrieve the island's index. If this index has not been marked as scene, we add it to the scene set and increase the potential size by the size of that island, as stored in island sizes. This ensures we only count each neighboring island once. After calculating the potential size for the current 0 cell, we update max island to the larger of its current value or the potential size. This loop continues for all 0 cells in the grid, ensuring we evaluate every possible flip. Once all cells are processed, the function returns max island, which represents the largest possible island size. The DFS helper function is used to calculate the size of an island and mark all its cells with a unique index. It takes the grid, the starting coordinates of the island, and the unique index as input. We use a stack to implement an iterative depth-first search. Initially, the stack contains the starting cell, and the size variable is set to 0. While the stack is not empty, we pop a cell from the stack and check if it is within bounds and still part of the original island, indicated by a value of 1. If so, we mark it with the unique index, increment the size of the island, and push all 4 neighboring cells onto the stack to continue the exploration. This process repeats until all cells in the island are visited. Finally, the function returns the total size of the island, which is used to update the island sizes map in the main function. Here, we're working with a small 2x2 grid. The input grid has 2 disconnected islands, represented by the 1s. Our task is to determine the maximum island size we can achieve by flipping 1 0 to 1. First, we initialize the grid size n equals 2, an empty dictionary island _ sizes to track the sizes of discovered islands, and a unique identifier index starting at 2. Next, we use a depth-first search, DFS, to identify all distinct islands. Starting at 0, 0, we find the first island of size 1 and mark it with index equals 2, updating the grid and island _ sizes to reflect this information. Then, we move to 1, 1, where we discover another island of size 1, marking it with index equals 3 and updating our data structures accordingly. At this stage, the grid now shows 2 distinct islands, and island _ sizes holds their respective sizes, 2, 1, 3, 1. Now that all islands have been identified, we move on to calculating the potential island sizes for each 0 cell. At 0, 1, flipping the 0 to 1 would connect the 2 distinct islands with indices 2 and 3. The neighboring indices are stored in a set called scene, which here contains 2, 3. Using the sizes from island _ sizes, we calculate the potential size as 1 plus island _ sizes, 2 plus island _ sizes, 3 equals 3. This becomes our current maximum island size, max _ island equals 3. Similarly, at 1, 0, flipping the 0 to 1 also connects islands 2 and 3, yielding the same potential size of 3. No other flips result in a larger island. Thus, the final output for this example is a maximum island size of 3. In this example, we have a larger 3x3 grid with more complex island structures. The process begins by initializing the grid size n equals 3, an empty island _ sizes dictionary, and starting the unique index at 2. Using DFS, we first identify the island at 0, 0. This island encompasses multiple connected cells and has a total size of 3. We update the grid to reflect this island with index equals 2 and record its size in island _ sizes as 2, 3. Moving on to 2, 2, we find another island, this time consisting of a single cell. We mark it with index equals 3 and update island _ sizes to include this new island, resulting in 2, 3, 3, 1. At this stage, the grid shows 2 distinct islands with their respective indices, and their sizes are stored in the dictionary. With the islands identified, we evaluate the potential island sizes for each 0 cell. Starting at 0, 2, flipping this 0 to 1 connects only island 2. The set of neighboring indices, seen, contains 2, and the potential size is calculated as 1 plus island underscore sizes, 2, equals 4. This becomes our current maximum island size, max underscore island equals 4. Next, at 1, 1, flipping this 0 to 1 connects both islands 2 and 3. Here, seen equals 2, 3, and the potential size is calculated as 1 plus island underscore sizes, 2, plus island underscore sizes, 3, equals 5. This updates max underscore island to 5. Other 0 cells in the grid do not result in larger islands, so the final output for this example is a maximum island size of 5. In this final example, the grid is already fully filled with 1s, meaning no flip is necessary. We start by initializing the grid size n equals 2, an empty island underscore sizes dictionary, and the index starting at 2. Using DFS, we identify the single large island, which covers all cells in the grid. This island is marked with index equals 2 and has a size of 4. We update island underscore sizes to reflect this, resulting in 2, 4. Since there are no 0 cells in the grid, there is no opportunity to flip any cell. Therefore, the maximum island size remains as 4, which is directly the size of the existing island. The final output for this example is 4. In analyzing the time complexity of our solution, we can break it into two main steps, identifying the islands and calculating the potential size of the largest island by flipping a 0. First, let's consider the process of identifying all islands. This involves performing a depth-first search, or DFS, starting from every unvisited cell that has a value of 1. During each DFS call, we traverse all cells that belong to a single island. Importantly, each cell in the grid is visited exactly once throughout all the DFS calls. If we let n represent the dimension of the grid contains n squared cells. Consequently, the time complexity for this part of the algorithm is O, n squared. Next, we calculate the potential largest island size. For every cell with a value of 0, we check its neighboring cells in all 4 directions. For each neighbor, we retrieve the size of its corresponding island from the island underscore sizes dictionary, summing up the sizes of unique islands. In the worst case, we iterate over all n squared cells, and for each 0 cell, we examine at most 4 neighbors. This also results in a time complexity of O, n squared. Combining both steps, the overall time complexity of the algorithm is O, n squared. Now let's analyze the space complexity. The grid itself has n squared cells, and since we modify it in place to mark visited cells during DFS, no extra space is required for tracking those visits. Next, we consider the island underscore sizes dictionary, which stores the size of each island. The maximum number of islands is n squared divided by 2, which would occur if each island consisted of a single cell. Therefore, the space used by the dictionary is at most O, n squared. For the DFS traversal, we use a stack to track cells, and in the worst case, the stack size can grow to the size of the largest island. If the entire grid is one big island, the stack size would be O, n squared. Additionally, we use a few auxiliary variables, such as the scene set and the directions list, which require constant space, O, 1. Combining these factors, the overall space complexity of our algorithm is dominated by the grid, the dictionary, and the DFS stack, resulting in O, n squared. To better understand the efficiency of our approach, we can compare it to a naive, brute force method. In the brute force approach, we would flip each 0 cell one at a time and perform a DFS or BFS to calculate the size of the resulting island. This would require n squared DFS operations, and each DFS would take O, n squared, time. As a result, the total time complexity would be O, n to the power of 4, which is highly inefficient for large grids. In contrast, our optimized approach pre-computes the sizes of all islands and stores them in a dictionary, eliminating the need to repeatedly traverse the grid. This optimization reduces the time complexity to O, n squared, which is much more practical. When analyzing the best, average, and worst cases, the results are consistent. In the best case, where all cells are already 1, only the first step is executed, resulting in O, n squared, time complexity. For the average case, where the grid has a mix of 0s and 1s, both steps are executed, but the time complexity remains O, n squared. In the worst case, with alternating zeros and ones requiring maximum computation, the time complexity is still O(n squared), as each cell is processed only a constant number of times. Finally, let's confirm the correctness of our big O bounds with a mathematical proof. The algorithm ensures that each cell in the grid is visited exactly once during the DFS phase and at most once during the evaluation of 0 cells in the second step. Since the grid contains n squared cells, the total number of operations scales linearly with the number of cells, resulting in O(n squared) complexity. Importantly, no operation in the algorithm introduces higher-order terms, such as n cubed or n to the fourth, which means our analysis is tight. This confirms that the overall time complexity of O(n squared) and the space complexity of O(n squared) are indeed accurate and optimal for this problem. When solving this problem, there are a few common mistakes to watch out for. First, overlooking edge cases can be a major issue. For example, you need to handle scenarios like empty grids, single-cell grids, or grids that don't contain any zeros. Missing these cases might lead to runtime errors or incorrect outputs. Another frequent pitfall is inefficient iteration. Using brute force on larger grids without optimizing can make your solution too slow, leading to time limit errors. Always look for ways to reduce unnecessary calculations, such as using memoization or implementing early exits. Next, be careful with grid modifications. If you're flipping a 0 to a 1 as part of your simulation, forgetting to revert those changes can cause unintended side effects, particularly in recursive or backtracking solutions. Additionally, it's crucial to respect connectivity rules. If the problem depends on connected components like islands, ensure you're accounting for the correct traversal directions, whether diagonal connections are allowed or not. Lastly, mismanaging coordinate bounds is another common issue. Accessing out-of-bound indices while iterating through neighbors can crash your program, so always validate coordinates before accessing the grid. Paying attention to these details will save you a lot of debugging time. Now, let's focus on some insights that can help you in interviews. Recognizing patterns in grid problems is an essential skill. Many of these problems revolve around familiar themes like connected components, shortest paths using BFS or DFS, or even dynamic programming. Spotting these patterns early can guide you toward the most efficient solution. Additionally, be mindful of trade-offs between space and time. For example, modifying the grid in place can save memory, but it can also make your code harder to debug. Think about whether clarity or performance is more important for the given context. Pre-computation is another valuable technique. By calculating auxiliary data structures such as prefix sums or visited matrices upfront, you can eliminate redundant work later on, making your solution more efficient. Finally, always test your code incrementally. Start with smaller grids or simpler cases to verify that your algorithm is working as expected before scaling it up to handle more complex or larger inputs. These strategies will not only improve your solution but also demonstrate to interviewers that you understand how to approach problems methodically. Finally, let's discuss related problems and alternative approaches. Some problems you might find helpful to practice include number of islands, which is a classic DFS or BFS challenge for finding connected components in a grid. Max area of island builds on that concept but asks you to compute the size of the largest connected region. Island perimeter, on the other hand, requires careful handling of grid boundaries and connectivity, while flood fill is a simpler traversal problem that can also be solved with DFS or BFS. Regarding alternative approaches, brute force is often the simplest to implement but becomes impractical for larger grids due to inefficiency. DFS and BFS are more suitable for exploring connected components, with DFS being memory efficient for smaller grids and BFS avoiding stack overflow on larger ones. Union find, or disjoint sets, is another powerful tool for dynamic connectivity problems, though it can be overkill for simpler scenarios. Finally, dynamic programming is a great fit if the problem involves overlapping subproblems or optimal substructures, such as finding paths or maximizing values in a grid. Choosing the right approach depends on the problem's constraints and what trade-offs you're willing to make between simplicity, performance, and space usage. Great work on completing this problem. To summarize, we discussed key strategies for making a large island, focusing on efficient handling of grid-based challenges. Remember to practice similar problems and analyze both time and space complexities. Thanks for watching, and don't forget to like, subscribe, and stay tuned for more problem-solving journeys. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!